Have you ever just stopped and wondered what is actually going on inside an AI chatbot when you ask it a question? It feels like you're talking to something intelligent, almost like magic. Well, it's not magic. And today we're going to pull back the curtain and show you how it really works. And it all starts with a surprisingly simple idea. So let's get right to it. The big question. How does an AI write a poem, or explain quantum physics, or even just answer a simple question? It's not thinking or understanding like a person does. Nope. The real process is actually a lot simpler, and frankly, a lot stranger than you might think. Okay, here's a great way to think about it. Imagine you've got a movie script. You see the user's line, right? But the AI assistant's reply has been torn right out. All you have is a blank space. Now, what if you had a machine whose only job was to look at a piece of text and make a really, really good guess about the very next word? Well, you could give it the user's question, and it would predict the first word of the answer. Then you'd take the question plus that first word, feed it back in, and it would predict the second word. You just keep doing that over and over and over again, word by word, until the response feels finished. That, at its very core, is exactly what is happening. And that brings us to the official term for this prediction machine, a large language model, or LLM. You can just think of it as a super sophisticated mathematical function. Its one and only job is to look at some text and predict the word most likely to come next. But here's the really cool part. It doesn't just pick one word. It actually gives a probability score to every single word it knows. Then it usually picks from the top options. That little bit of randomness is why you can ask the same question twice and get two completely different yet still coherent answers. So you've got to be wondering, right? How does a machine get so ridiculously good at this next word prediction game? Well, the answer is all in the first step of its creation, training. And the scale of this training is just truly hard to wrap your head around. The model's entire education comes from reading. And I mean reading. It crunches through a colossal amount of text. Books, articles, Wikipedia, Reddit, you name it. Basically, it's absorbing a giant snapshot of the public internet. From all that data, it starts to learn the patterns, the grammar, the facts, the relationships between words, everything. And when I say colossal, I mean, let's put it in perspective. If you, a human, decided to read all the text that was used to train just one of the earlier models, GPT-3, and you read 24 hours a day, 7 days a week, without stopping, it would take you over 2,600 years. And guess what? The new models are trained on way, way more data than that. It's an absolutely incomprehensible amount of information. So here's how it actually learns from that mountain of data. Picture the model as this giant machine with billions of tiny little dials on it. These are called parameters. When you start, all those dials are set to random, so the model just spits out total gibberish. But during training, you show it a sentence but hide the last word. The model takes a guess. Then you show it the real word. If the guess was wrong, an algorithm goes back and slightly adjusts all those billions of dials to make it a little more likely to get it right the next time. Now, just imagine doing that trillions of times. And if you think the data is staggering, the amount of pure number crunching to turn all those dials is even more insane. Let's say you were a human calculator who could perform 1 billion calculations every single second. It would still take you more than 100 million years to do all the math required for the training. The only reason this is even possible is because of special computer chips that can do tons of calculations at the same time, in parallel. And that very idea, the need for parallel processing, leads us straight to the secret engine that really made all of this possible. It's a brilliant piece of engineering called the transformer. See, before 2017, older models had to read text just like we do, one word at a time, in a straight line. It was logical, but it was incredibly slow and created a huge bottleneck. Then, in 2017, researchers at Google introduced the transformer, and it completely changed the game. Its design lets it look at all the words in a sentence, or even a whole paragraph, at the exact same time, in parallel. But this isn't just about being faster. Processing everything at once is the key to a much, much deeper understanding of context. Let me show you what I mean with a really simple example. Let's just take an ambiguous word like bank, right? It could be a place you put your money, or it could be the side of a river.
Now, an old model would see the word bank and have to remember the context from earlier in the sentence. But a transformer sees the word bank and the phrase near the river at the exact same instant.
And because it sees everything at once, it can figure out the true meaning. This is its core superpower, a mechanism called attention. It lets all the words in a sentence talk to each other at the same time and refine each other's meaning. The word river basically tells the word bank, hey, we're not talking about money here. This all-at-once understanding of context is what makes these models so powerful. Okay, so at this point, we have a model that is an absolutely incredible word predictor. It's learned from the entire internet. But being great at predicting the next word of some random internet forum post is very, very different from being a safe and helpful assistant. And that's where a second crucial training phase comes in. So let's break down these two main stages. Phase 1 is pre-training. That's what we've been talking about, learning language by predicting words on that massive internet dataset. But then comes phase 2, fine-tuning. This often uses a technique called reinforcement learning with human feedback, or RLHF. Basically, you have actual human workers who chat with the model. They rate its responses, they flag things that are wrong or unhelpful or toxic, and all of that feedback is used to tweak those dials just a little bit more, teaching the model the patterns of how to be a useful assistant, not just an internet autocomplete. All right, we've arrived at the most fascinating and, honestly, maybe the most mind-bending part of this whole thing. Where does all this incredible fluency, this ability to reason and write poetry, where does it actually come from? The wild part is this. No one sits down and programs the rules of grammar. No one codes a module for how to be creative. Instead, all of these complex, amazing abilities are what's known as an emergent phenomenon. They are the completely unexpected byproduct of that one simple goal: predict the next word, combined with billions of those little dials and trillions of examples. The complexity and the capabilities just emerge from the sheer scale of it all. The end result is something that, as one of our sources put it perfectly, is uncannily fluent, fascinating, and even useful. And that emergent behavior is what creates that feeling of magic we started with. It's not programmed intelligence in the way we usually think of it. It's more like patterned intelligence, scaled up to a degree that is almost impossible to imagine. And that, of course, leaves us with a final, massive question to think about. When the most powerful and interesting behaviors of a technology are not directly designed by anyone, but simply emerge from the process, what does that really mean for its future? It highlights the incredible potential we're unlocking, but also the profound challenge we face in trying to understand and guide what we've actually created.